Hello, my name is Gavrovska, and today's topic is video-based assistance for autonomous driving. Authors of this paper are members of the group for digital image processing, telemedicine and multimedia at Faculty of Electrical Engineering, University of Belgrade. First, I will give a short introduction on autonomous driving. Then some driving parameters will be mentioned, as well as driver behavior monitoring techniques. Finally, some experimental results followed by conclusions will be presented. We all know that autonomous driving is extremely popular topic, and nowadays vehicles are considered as test platforms for experimenting with new ICT technologies, various sensors, automation control, and artificial intelligence. Here are some numbers. World Health Organization reports that about 1.35 million people die in road accidents each year. And the idea is to halve the number of both deaths and injuries by 2030. And autonomous driving and driving assistance systems, services, and applications are expected to help with this issue. Moreover, Intel reports about 40 terabytes of data for every 8 hours, and that's a lot of data that we are dealing with. There are 6 driving automation levels, from level 0 to level 5. At level 0, driver has full control of a vehicle, whereas at levels 1 and 2, some controls are performed automatically. Driver is still in charge. And at levels 3 and 4, a machine is taking into account some environmental parameters and performs automatic tasks, where a driver is included in decision making. Finally, at level 5, a driver can relax since a fully automated vehicle is developed. Many questions need to be answered. For example, is it wise to give up some drivers' responsibilities? Or how much assistance do we actually need? Or what is usual and unusual behavior? Drivers' feedback on comfort is useful for experiments, but it may depend on the level of tiredness or age. On the other hand, 5G technologies, Internet of Things, artificial intelligence are significantly changing smart environments. Another important question is where to perform data processing. Is it on cloud or some supervisory level? Or is it on board or at some edge? And multimodal sensing, road mapping, and vehicle control are processes that are going on. For example, when we are talking about vehicle surrounding and road mapping, it is not just about road edge detection. It is also about road surface and pavement quality. And one of the most useful parameters is International Roughness Index. The roughness index is popular throughout the literature, and one of the papers shows high correlation with heart rate variability and speed, and this is again highly related to comfort level. In a vehicle, we already have driver assistance, like seatbelt reminders or GPS road mapping, and state-of-the-art head-up displays and augmented reality applications may provide new road mappings. Various features are already being used for monitoring driver behavior, like ECG and EEG characteristics. And drowsiness monitoring, for example, uses head nodding, as well as eye tracking and gaze parameters. Particularly interesting are head-related applications and RGBD cameras, where D stands for depth. Sudden speed changes are related to both head position and comfort level changes, and long distance laser methods are used for out of the vehicle monitoring. Short distance ones can be used for both face detection and head position monitoring. Here we analyze two different data types. We analyze roughness parameter changes and head position changes. Roughness parameter is measured using special vehicle with inertial sensor, and it measures at 100 meters step. This is a standard procedure. And head position changes are also monitored in laboratory conditions using astro-orbit RGBD camera with appropriate software development kits for tracking specific nodes. It's a kind of Kinect-like camera. It is placed on a laptop as typical web camera, only focusing on upper part of the body, as it is placed in upper left corner of a cabin. And 5 individuals participated and simulated sudden head-down, head-up movements. Some of them can be interpreted in further analysis as false alarms, and some of them can be interpreted as, for example, neck fractures, since they are quite common when comfort level is changed. Here are some of the results for roughness measuring. Most of the measurements are in upper 2 classes, but one can detect abrupt roughness changes that we are talking about here. In this example, the change of 4 comfort levels are considered as significant. Then we tested RGBD camera possibilities. Links 119 and 19.2 are valuable for head and neck position, as presented here. And this is a notation used by astro-orbit camera. In figure 6, 2 sudden head-down and head-up movements are shown, and this can be observed as 2 false alarms. Different camera positions are tested, but we chose co-driver seat or side position. Here we present some of the results of alpha range, up-down movement interval, and down-up movement, and it takes roughly about 0.2 to 0.4 seconds for sudden head-down movement, and 0.3 to 0.6 seconds to return head in initial seat. So we proposed a procedure for dealing with such movements, namely when a significant change occurs, the tracking starts, and when local minimum is reached, a comparison to the triggering moment is made in order to check whether it is a sudden head-down movement. Based on an experiment, further tracking should last for about 0.6 seconds, so we are still under 1 second. And during the head-up movement, 75% of initial trigger alpha level should be reached. If not, something is wrong and the alarm is activated. For the camera model used here, there is about 0.6 meters distance, and some models can be used even for shorter distance, about 0.4 meters. And even though most of the literature is considering 3D models of vehicles and pedestrians out of the vehicle, 3D skeleton can be used as well for in-vehicle environment. And it is possible to detect both roughness and head-down changes. Moreover, roughness parameter can be used for setting higher priority in video monitoring. Of course, it should be decided when and where such data should be processed to have a whole environmental context. Thank you for your attention. And we got two TPC questions. The first one is, what are the steps required to bring the solution out of the lab and put it one step closer to the deployment? Well, the camera and adequate hardware for processing data should be placed in a car. After that, the roughness data should be used accordingly. For example, the roughness parameter can be used for triggering the camera. And the second question is, can you devise a simulation environment where your solution could contribute to, for example, driver modeling in specific driving scenarios? That's a nice question. The answer is yes and no. It's not possible to have a real-life simulation in order to simulate some injuries, or it's not ethical, at least. But some simulation environments can be developed, as in the case of experimenting with seat belts and experiments with airbags. So monitoring can be performed using a doll when a crash or sudden steering or braking happens. There are standardized procedures that are used in such cases. I hope this answers your question. Again, thank you for your attention and stay well.